names. Did anybody get the next one? Oh, we were past this? Sorry.
Yeah. I think we were by hydrogen phosphate.
Okay, here. Did we already name these?
Yeah.
Oh, okay. Just as quick. All right. And I talked about the conjugate relationship.
Sort of.
Conjugate relationship means we don't need two separate charts. We have one chart for both acids and bases. What happens is when HClO4 loses the hydrogen ion, it forms ClO4 minus. ClO4 minus itself is a base. It's capable of accepting a hydrogen ion and go back. So we can go back and forth here just by losing a hydrogen ion or gaining a hydrogen ion. And so losing a hydrogen ion are acids, gaining a hydrogen ion are bases. So what we have is a chart of acids here, but we also have a chart of bases. And there's something called the conjugate relationship. That is, if we have a strong acids lose the hydrogen ion easily. That means if we lose the hydrogen ion easily, who lost it? Perchlorate lost it. So perchlorate doesn't have a high affinity for hydrogen ions. If it doesn't have a high affinity for hydrogen ions, it's a weak base. So in other words, a very strong acid makes a very weak base as its conjugate. And so the strongest acid on the chart is perchloric acid. The weakest base on this chart is perchlorate. Then we go to the other end. At the other extreme, we have the strongest base on the chart. The strongest base on the chart is methide. And the weakest acid on the chart is methane. Methide. And so this conjugate relationship is useful. So let's take a look at the bases. Let's name the bases. I think we already named them up to here, right? This is where we left off, somewhere around here. And so this was methide, hydride, oxide, here's where I try to emphasize the pattern. Methide, hydride, oxide. What's this one? Well, my guess would be ammoniumnide, or ammoniumnide, but that's too much. Ammonide? No, it doesn't sound right. Well, let's cut down the number of syllables. We'll go with amide, or just get rid of the am and just go with ide. What do you think it is? It's amide, ammonia-ide, right? Amide. Amide's important because do you see that acid-base chart over there? What's the strongest base on that chart? And it's hard to see, but somebody name the strongest base on that chart for me. No, the other side. NH2 minus. NH2 minus is called amide. That's it. Amide's the strongest base on that chart. It's not the strongest base on this chart, though. This is a very exotic species here. What's most common is hydroxide. That's But we have amide. What's this one called? Sulfide. This one? Hydroxide. How about this one? Phosphate.
Carbonate.
Phosphate's borderline strong base. A lot of laundry detergents have phosphate in them. Yeah, carbonate, it's good. What's this one? Cyanide. So if it's a strong base, like hydroxide, sulfide, etc., these have a high affinity for hydrogen ions. These want to take hydrogen ions. So these are good powerful bases. But these are pretty strong too, but we would classify these as weak bases. But on the weak base spectrum, these are on the stronger side. Like phosphate is very close to hydroxide in terms of strength, but we still call phosphate a weak base and hydroxide a strong base. It's just because there's a border line here. This is the border line. And so everything on this side of the border is weak, everything on this side of the border is strong, but there's levels to it. All right, so we got phosphate, carbonate, cyanide, ammonia. Now, ammonia is what we call amphoteric species. Amphoteric or amphiphilic species can go either way. You can either act as an acid or act as a base. And so this is why this is deja vu, because we saw ammonia before. Down here, but this ammonia is behaving differently than this ammonia up here. This ammonia is donating a H plus to form amide or amide. This ammonia is accepting an H plus to form ammonium. So ammonia can either donate a proton or hydrogen ion, or can accept the hydrogen ion. It forms different products depending on what it does. It's a much better base than it is an acid. As far as the acid side of ammonia goes, it's so bad that nobody ever considers it an acid, really, unless you're working with extremely powerful bases. It's a moderate base, decent base. This one, monohydrogen phosphate. Not as good as phosphate. What's this one called? Here. Not sulfide. It's hydrogen with sulfide, which we call hydrogen sulfide. We got to be careful, because hydrogen sulfide, somebody might think it's H2S. So we have to call that the hydrogen sulfide ion, not just hydrogen sulfide. Most of the others, we don't have to use the term ion. Carbonate's always an ion. This one, bicarbonate or hydrogen carbonate. This one, acetate. This one's called formate. So it's like acetate from acetic acid. It's formate from formic acid. This one, fluoride. Fluoride turns out to be a decent base compared to chloride, bromide, and iodide. Chloride, bromide, and iodide are very bad bases, but fluoride's pretty decent. This is why HF is a weak acid. This one, nitrite. This one, you don't worry about. This one you do in Chem 1B. This one, dihydrogen phosphate, sulfate. This one is called trichloroacetic acid, or trichloroacetate. On the left is trichloroacetic acid, on the right is trichloroacetate. It's the base. Next is water. Now water is interesting because water is on both sides of the chart as well. Here we have water. Here. Down here we have water on the opposite side. Water is interesting in the respect that it can go either way. There's no preference. It could either act as an acid like this, or it could act as a base like that. Whereas ammonia has a preference. Ammonia much prefers to be a base. The same thing with monohydrogen phosphate. Monohydrogen phosphate can go either way. It's an acid or a base, but it's a much better base than it is an acid, so it prefers base. That's what we want to do. We want to be able to figure out how we can tell. And so the initial part of this is just to look at the data. And then we try to see, what are some common features that might indicate to us it's a strong acid or strong base. And as we dig deeper into it, yes, there's something that all these strong acids share in common. There's something that they do. But it's not just one thing. Because if you just base it on one factor, then you could get certain things wrong. There are multiple factors that we look at when we consider acid-base strength. And so this is why, for example, we'll just look at a series like, HBr, HCl, HI, something like that. We'll look at that series, and then we'll look at another series, and then C. And so there's definitely some clues that you can get from just looking at it. For example, I know that phosphate is going to be a much more powerful base than monohydrogen phosphate and dihydrogen phosphate and so on. That's because monohydrogen phosphate has already gained a hydrogen ion. Dihydrogen has already gained 2, that kind of thing. So there's simple things, and then there's more in-depth stuff that we can look at as far as the structure goes. So for example, trichloroacetic acid is going to be a much more powerful acid than acetic acid. So what impact is putting these 3 chlorines on this carbon have? And so those are the types of things we look at later on when we get into structure. But there are structural reasons why. But for right now, you want to just familiarize yourself with the trends and behavior. And then we'll look more at the structure. Well, just continuing, just name that bases for me. Nitrate. It turns out that these conjugate bases of the strong acids are so weak that nobody really considers nitrate basic. It's just too weak. This one, chlorate, getting even weaker. This one, hydrogen sulfate or bisulfate, chloride, bromide, iodide, perchlorate. So, for example, sodium chloride. When we're thinking about the acid-basic properties of sodium chloride table salt, it's not significant. So we could have a table like this. And somebody might say, "Oh, chloride's a base." But just having a table like this, you have to be able to interpret, the table. And so this is what we're doing. First, we're going to look at the table. We want to be able to at least name everything in the table, or skip. We'll skip some of these because they're beyond the scope of the class. And then just kind of get familiar with the table. Some people ask me, do you need to memorize? No, you don't need to memorize this table. But, it would be a bad decision to completely ignore the table as well. A lot of people, if they don't have to memorize the table, they can always look it up. They can look it up. But when they come back to look it up, they don't understand the little nuances, the interpretation of the numbers. And so that's what we're trying to gain here at this point. We're trying to get a feel for this, just a little bit at a time. Not going to put too much information just yet. And so, okay, well, that was our first run through the table. So we have an idea. And you should, I told you not to memorize the whole table, but you should memorize something. What should you memorize out of this? Yeah, the 7 strong acids. Somebody asked me, do you have to memorize the order? No. But it's not a bad idea to know the strongest. What's the strongest acid? For Clark, what's the strongest base? Well, it depends on what chart it is. All right, so that's some acid base. We just look at the chart pretty much when we want to figure things out. And when we're looking at reactivity, an acid donates a proton or hydrogen ion, a base accepts it. And did I give you some examples of acid-base reactions? No? Didn't give you any examples? Okay. Let me give you some examples of some acid-base reactions. Let's take an acid, probably the most common acid is this. This is called hydrochloric acid. Probably the most common base is this. This one's called sodium hydroxide. Hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. So we expect a vigorous reaction between the two. And what forms, it's like a metathesis reaction. The hydrochloric acid has H+. The sodium hydroxide has OH-. And so the H+ and the OH- come together. The HCl is the H+ donor, the sodium hydroxide is the hydroxide, or proton acceptor, or hydroxide donor. And so what happens is those two come together and we form water and sodium chloride. So this kind of looks like a metathesis reaction. A metathesis reaction, we swap the partners, and so it would be hydrogen ion going with hydroxide. Hydrogen with hydroxide is just water. It would be sodium ions going with chloride, so that would be sodium chloride. And indeed, it is a metathesis reaction, but this one has the characteristics of an acid base as well, so we can classify it either as metathesis or an acid base. There are some reactions that aren't like metathesis reactions. Metathesis is just favorable ion combinations. An example of that would be something like HCl plus ammonia. HCl has a cation H+ and an anion Cl-, but ammonia really doesn't. Ammonia is just a molecule. And so in this case, ammonia can accept. If ammonia accepts a proton, we end up forming ammonium, and then we have the chloride left over, so we end up with ammonium chloride here. And so just a couple of examples of some acid-base reactions. The next type of reaction that we're going to look at is redox. So I should say that acid-base reactions are proton or H+ transfer reactions. Metathesis are favorable ion combinations. And the third type of reaction is redox. Redox stands for oxidation reduction. Did I talk about it, redox at all? Did I talk about oxidizer, reducer, that kind of thing? A little bit? So what we're going to do is we're going to look at the redox chart. Oxidizers are electron poor species. Reducers are electron rich species. The more poor, electron poor it is, the more powerful of an oxidizer. The more electron rich it is, the more powerful of a reducer it is. And so we're going to look at the chart here. It turns out the most electron poor species on the chart is F2. F2, this is the most electron poor. This is going to be the strongest oxidizer or oxidizing agent. So right now we're just looking at the patterns and the trends, but why is fluorine such a powerful oxidizer? Why does fluorine want electrons? Fluorine wants electrons because it's just one electron short having that neon. It's 9 electrons. It contains just one electron would be like neon. So all of them, fluorine, chlorine, bromine, iodine, all those should be decent oxidizers. So here we have fluorine. Fluorine taking 2 electrons to go to fluoride. Here we have chlorine doing the same thing. So chlorine's a decent oxidizer, but fluorine's much better. So fluorine, which is also a gas. Below there, we're going to get to bromine. Bromine, which is significantly weaker than chlorine, which we have there. So we have bromine gaining 2 electrons from bromide. And then we'll continue down to iodine. And so fluorine, chlorine, bromine, and iodine, all those are oxidizers. All those are considered electron poor, but fluorine would be the most electron poor out of all of them. And one way of thinking about that is, well, what causes fluorine to be more electron poor? Because all of them are just gaining 1 electron, whether it's actually after dissociation. Right here we have, actually there's 2 electrons, but each chlorine atom is gaining 1. So if we break that apart, we have 2 chlorine atoms, and then each one gains 1 electron to form those 2 chlorides there. So, what makes fluorine a better oxidizer than chlorine? The size? The size. I mean, fluorine's pretty small, so it's pretty good at attracting an electron. How many does oxygen typically like to gain? Fluorine likes to gain 1. How many does oxygen like to gain typically? Well, fluorine forms the F minus. Oxygen would form the O2 minus. Right? And so fluorine likes to gain 1. Oxygen likes to gain 2. And so this is oxygen, but this is another form of oxygen. The most common form of oxygen is O2. This one's less common. It's O3. O3 is called the layer up there, the ozone layer. This is ozone. In ozone, we have 3 oxygen atoms. 2 of them, nothing happens to, but one of them gains 2 electrons. So. But this is kind of weird. I'm saying that these species are electron poor. These species are oxidizers, but this one already has 2 extra electrons. This is S2O8 2 minus. There's 2 extra electrons. Why does it need more electrons? And the same thing down here. Permanganate. It has a negative charge. This one, Cr2O7. What's Cr2O7 again? Dichromate. That's -2 charge. A lot of these have negative charge. Why do they want more electrons? Well, that's something we have to think about. and try to figure out what's going on with that. All right, so right now, let's go ahead and start naming these, just to get familiar with the table. Start